Hey everyone, and welcome back to the Deep Dive. Ever wonder how these incredibly smart language models actually read text? Today we're plunging into a really groundbreaking new paper. It could totally change how AI processes information. Moving beyond old methods to something truly end-to-end, our mission in this deep dive. To unpack dynamic chunking for end-to-end hierarchical sequence modeling, this paper really challenges a long-standing practice in AI tokenization.
That's right. And the core problem, the thing we're really looking at here is that even with amazing progress like the transformer architecture, models still rely on something pretty old school, fixed vocabulary tokenization, like byte pair encoding, BPE. Think of it like a manual preprocessing step. It's kind of been stuck there, handcrafted, while everything else in AI raced ahead.
And this old way has problems, right?
Oh, yeah, definitely. Well-documented issues. Things like poor understanding of individual characters. The tokens themselves often lack real meaning. They're just statistically common chunks. So interpretability suffers. And performance can really take a hit, especially with complex languages or even other kinds of data, not just text.
Okay, so if we want these truly foundation models, the kind that learn straight from raw data without these predefined steps, how do we actually get there? That seems to be the central question this paper tackles. Because for a long time, tokenization felt, essential, didn't it?
It did, absolutely.
Why was that? Was it just speed?
Mostly, yeah. It's really good at compressing data, shortening those long sequences. If you're dealing with massive data sets, making them smaller, more manageable for the computer, that's a huge boost for computational efficiency.
But people tried to get around it before, didn't they?
Oh, many times. But they ran into some serious walls, like trying to model directly at the byte level. Think reading every single letter. Architectures like Mama Byte tried this, but the computational cost was just prohibitive. And even then, they didn't perform as well as the tokenized models comparing compute.
So just reading bytes wasn't the answer. What else?
Well, there were hierarchical ideas, but early attempts were maybe too simple, like just compressing every few inputs. But that's not data dependent, right? It doesn't adapt. Human language has variable information rates, so that kind of fixed chunking doesn't work so well.
Okay.
Then you had smarter strategies trying to find chunks based on, say, spaces or entropy like space byte or byte latent transformer. But these weren't truly end-to-end. They still needed other tools, external predictors, to figure out where the boundaries should be, often specific to just one data type, too.
And the really big hurdle.
The toughest part was getting the model to learn where to make those discrete cuts, the boundaries, without explicit supervision. Optimizing that kind of selection process, it's tricky. It led to unstable training. That instability basically stopped people from scaling these ideas up or building deeper, multi-level hierarchies.
So it sounds like the core challenge was integrating this chunking into the model learning process itself while making it efficient, learnable, and crucially stable enough to scale up.
Exactly. And that's where HNet comes in. It's proposed as an end-to-end hierarchical network. It compresses raw data using a recursive process they call dynamic chunking, or DC, and it's data dependent.
Okay, dynamic chunking. So it learns how to chunk.
Precisely. The aim is to match the efficiency of the old tokenized pipelines, but significantly improve the model's actual understanding. It replaces those handcrafted rules, those heuristics, with segmentation that's aware of content and context, learned purely from the data.
Interesting. So what does the HNet architecture look like? You mentioned hierarchical.
Yeah, structurally, it's a bit like a UNet, which people might know from image processing, but adapted for sequences. You've got encoder networks, a main network in the middle, and then decoder networks.
And it's recursive.
That's a key part. The main network can actually be another HNet, so you can stack these hierarchies. This lets the outer stages handle fine-grained details, the raw stuff, while inner stages work on coarser, more compressed info. Kind of like traditional tokens in a way, but learned dynamically, not predefined.
Right. And how did they design these different parts? Any key principles?
Yeah, a few things stood out. For the encoders and decoders, the parts dealing with the long, raw sequences using state space models, or SSMs, specifically Mamba 2 layers, was a big win. They're really efficient for long sequences and seem to have an inductive bias that helps with compression.
Okay, so SSMs for the outer layers.
Yeah.
What about the main network?
That's where most of the model parameters live. It works on the already compressed sequences, so it can be more computationally intensive. And it's flexible. You could slot in a transformer there or potentially other architectures.
And architecture-wise?
Generally, the model width, the dimensionality, tends to increase as you go deeper into the hierarchy. And because those outer SSM layers are efficient, you might not need as many of them.
Got it. Let's get into the core of it then, this dynamic chunking mechanism.
Right.
How does the model actually learn where to put the boundaries?
Okay, so the DC mechanism is really the novel engine here. It learns segmentation end-to-end using standard optimization, which is pretty neat. It boils down to two main techniques working together. First, there's the routing module.
Routing module.
Think of it like this. It looks at adjacent bits of data, compares their representations using cosine similarity. If the similarity is low, that suggests a change in context, right?
Right.
So it predicts a high probability for a boundary there.
Okay, so it senses changes. What's the second technique?
That's the smoothing module. This tackles a fundamental problem. Boundaries are discrete, they're either there or not, but neural networks learn best with smooth, differentiable changes. So this module transforms those hard boundaries into something smoother. They use an exponential moving average, an IME interpolation. This makes backpropagation work effectively. It also helps stabilize things by smoothing out uncertain chunks using context from before, kind of like adaptive error correction.
That sounds crucial for making it trainable.
Yeah.
Are there other parts supporting this?
Yes, a few helpers. There's a downsampler. It basically takes the output from the routing and smoothing and keeps only the vectors where a boundary was flagged. That's how it compresses the sequence. Then an upsampler does a reverse for decoding, using confidence scores to expand the sequence back out while keeping the flow. They use something called a straight-through estimator, or STE, here to help with learning.
And you mentioned keeping the compression balanced.
Right, that's the ratio loss. It's an extra loss function, kind of like a nudge. It guides the model towards a target compression ratio, stopping it from just, compressing everything to nothing or not compressing at all. A bit like load balancing you see in mixture of experts models.
Okay.
And they also integrated other techniques, standard stuff, but important for stability. Network normalization, careful use of projections, modulating learning rates for the hierarchy, all to make the end-to-end optimization work reliably.
And so conceptually, it sounds really well thought out, but the proof is in the pudding. How did HNet actually perform, especially compared to those strong, established tokenized models?
Yeah.
They did rigorous comparisons, controlled for data and compute.
They did, and the results are, well, quite compelling. A single-stage HNet, working straight from bytes, managed to match the performance complexity and downstream tasks of a strong BPE transformer once they got over about 1 billion parameters. And qualitatively, it learned sensible boundaries, compressing data similarly to BPE, but without being told how.
Just by learning from the data.
Exactly. Then they tested a two-stage hierarchy, HNet two-stage. This version scaled much better with data. For their XL scale models, the two-stage HNet actually overtook the tokenized transformer after only 30 billion training bytes. And that performance gap just kept widening as training went on.
Wow, so it learned more efficiently from the data stream.
It seems so. And even at a slightly smaller, large scale, the two-stage HNet matched the average downstream performance of the bigger XL BPE transformer.
That's impressive scaling. What about robustness? Tokenizers can be brittle sometimes.
That was another interesting finding. Without any special training data, the pre-trained HNet was significantly more robust to noisy or perturbed text. They tested this on a suite called Noisy Hellaswag, and HNet handled the messiness much better than the token-based transformer.
And interpretability. Did the learned chunks make sense?
Yeah, this was quite cool. Visualizations showed it automatically finding semantically coherent units. It puts boundaries at spaces, sure, but the two-stage version learned more. It chunked whole words, numbers. It even grouped related words together, like the backbone or such as, into single chunks. And importantly, it could often find word boundaries even if the spaces were missing a classic tokenizer problem.
That ability to find structure without explicit delimiters like spaces seems powerful. Did it work well on languages without clear spaces like Chinese?
Yes, the improvements were actually more pronounced there. On Chinese language modeling, the HNet two-stage significantly outperformed simpler HNets and the Llama 3 tokenized transformer. Their accuracy on a benchmark called X-Winograd's jumped quite a bit.
How about other data types? Code, biology.
Strong results there, too. For code, both HNet versions beat the BPE transformer significantly. On DNA sequences, they performed similarly to other byte-level models, but were much more data efficient, needing roughly 3.6 times less data, and the ablation studies, where they turned off different parts to see what mattered most.
Yeah, what did those show?
They confirmed the smoothing module was essential for stable training. The similarity-based routing and the STE for the upsampler were also key. And interestingly, those Mamba layers in the encoder-decoder were crucial, even if you fed them BPE tokens, suggesting their architecture is just inherently good for this kind of compression task. They also found HNet's dynamic chunking was way more effective than just using generic sparsity methods like mixture of experts.
Okay, so wrapping this up, what's the big takeaway here?
Well, I think HNets really introduce a new class of foundation model architecture. The key is they potentially allow us to finally remove those fixed tokenizers. The model learns that preprocessing layer itself end to end.
Learning directly from the raw data stream.
Exactly. And this capability, driven by that dynamic chunking mechanism, leads to models that seem to substantially fix issues with traditional tokenizers. They show really strong performance across different languages, different modalities even, and they're fundamentally designed to do more learning with less handcrafted preprocessing baked in upfront, more inherent understanding.
It's fascinating stuff. A move towards AI that learns more like, well, maybe more like we do, directly from the flow of information. Thanks for joining us on this deep dive into HNX and the future of end-to-end language modeling. Lots to think about there.